Okay, in this video I'm going to show that the geometric random variables are memoryless, and we'll have to talk about what memoryless is, and I didn't talk about this when the geometric random variables were introduced because we need the idea of conditional probability to be able to define memoryless. But I want to remind you that for a geometric random variable, the probability that x is k is 1 minus p to the k minus 1 times p. And this is a waiting time random variable, and it gives the number of trials you have to perform before an event occurs for the first time. Okay. So this probability would be the probability that you have to do k trials to get one occurrence of the event. And k is going to be some positive integer, 1, 2, 3, etc. And p is a probability, so it's some number between 0 and 1. Well, let's suppose that the event does not occur in the first n trials. What is the probability, or so in some positive integer, what is the probability that it will take m more trials, so m some other positive integer, for the event to occur? And as I mentioned earlier, we're dealing with a conditional probability here. So this is a question, so it needs to end in a question mark. And what are we trying to compute here? Well, we're trying to compute a conditional probability. There's something that's going to go over here. Now, what are we conditioning on? We're assuming that the event does not occur in the first n trials. Since x is a geometric random variable, it gives the number of trials that it takes for an event to occur. So this is just saying that it takes more than n trials for the event to occur. So given that x is greater than n, what's the probability that it will take m more trials for the event to occur? In other words, what's the probability that it takes a total of n plus m trials for the event to occur? Well, using our formula for conditional probability, we see that this is the probability that x is n plus m, and x is bigger than n, all over the probability that x is bigger than n. So n and m here are going to be positive integers. That's important. And actually, you can have 0 for n and m, but we'll stick with positive. Okay, well, on top, if these are indeed non-negative integers or positive integers, then the condition x equals n plus m is more restrictive than x is greater than n. Since m isn't negative, if the first is the case, then the second one will always be the case. So this is just the probability that x is n plus m. And then the bottom is the probability that x is greater than n. Now, since we have a formula for this random variable's distribution, we can write out summation for this probability on the bottom, and the one on top is just to plug into that formula. So the probability that x is n plus m is, we just plug n plus m in there, and we get 1 minus p to the n plus m minus 1 times p, and then on the bottom we have the sum from k equals, let's see, we'll want to start at n plus 1. I want to sum up all the probabilities starting at n plus 1 to infinity of 1 minus p to the k minus 1 times p. And then that gives us a quotient that we're going to simplify using Wolfram alpha. So I'm going to pull up Wolfram alpha here. And actually I think I'll just use Wolfram alpha to simplify this sum for me. Okay, so we're doing the sum of 1 minus p to the power of, did it again, k minus 1 times p. And we'll do that from k equals n plus 1 to infinity. Press enter. And we find that this sum is just 1 minus p to the n. And it turns out there's actually a logical explanation for why that is the case. Let me switch back over to the blackboard here. Okay, when I sum up these terms from k equals n plus 1 to infinity, notice that I'm summing up a bunch of probabilities. This is the probability that my random variable x is bigger than n. So I could have computed this by just finding the probability that the first n trials do not result in a success, did not result in the event. Well, that's just 1 minus p to the n, since each of the trials does not result in the event with probability 1 minus p. Okay, so I'm going to need to go up here. I'm running out of space down here. And what we have is, let's see, I got 1 minus p to the n plus m minus 1 times p. So we're now going up here. All over 1 minus p to the n. Okay. And this is 1 minus p to the, let's see, the power of n's will cancel, and that's just m minus 1 times p. And notice this is exactly what we get when we plug m into the formula for the distribution. This is just the probability that x is m. Okay, so I'm going to erase all this work in between, and we're going to talk about what it means for the random variable x to be memoryless. So let me erase that here. Okay, so we found that the probability that x is equal to n plus m, conditioned on x is greater than n, is just the probability that x is equal to m. Okay. This is what it means for the random variable to be memoryless. If we already know that that we've weighted n trials, well then that doesn't really change anything. The probability that we weight m more trials is the same as the probability that it takes m more trials to begin with. The fact that n trials go by without a excess does not affect the upcoming trials. So this means the random variable x is memoryless. And it turns out that none of the other random variables in this course are memoryless, at least none of the other discrete random variables. We will run into a continuous random variable that's also memoryless, and that is the exponential random variable, and I think it's going to be a homework assignment for you to prove that the exponential random variable is memoryless, but you don't have to worry about that for at least a few weeks here.